close your eyes and imagine a world you've never seen. Not because it's far away, but because it vanished 12,000 years ago. A world so alien, so impossibly different from today, that if you were dropped into it, you wouldn't recognize Earth at all. The year is 10,000 BCE. Ice sheets tower over the northern states, miles thick, heavier than mountains, grinding slowly southward like frozen bulldozers reshaping the world. In North America, ice covers everything from the Arctic Ocean down to where New York City will one day stand. In the Pacific Northwest, glaciers bury Washington, Oregon, and most of Idaho under crushing walls of white. The weight is so immense that the continents themselves are pressed down, sagging under billions of tons of frozen water. The oceans are 400 feet lower than today. Not 40 feet. 400. Walk where Miami's beaches will someday be, and you're 60 miles inland. The Florida Straits don't exist. Florida and Cuba are nearly connected by rolling grasslands. The Caribbean isn't a chain of islands, it's part of a massive landmass. You could walk from Alaska to Russia across a land bridge wider than Texas. And the cold, the brutal, relentless cold that defines everything. Average global temperatures are 10 to 15 degrees Fahrenheit lower than today. That might not sound like much, but it's the difference between civilization and ice age, between cities and survival. But here's what makes this world truly breathtaking. The animals. Creatures so massive, so powerful, they make today's wildlife look tame. Woolly mammoths, 13 feet tall at the shoulder, with curved tusks 15 feet long, roaming in herds across the frozen grasslands. Giant ground sloths the size of elephants, standing on their hind legs to strip branches from trees. Saber-toothed cats with 8-inch fangs, perfectly designed for puncturing thick hide and massive muscle. Short-faced bears that weigh 3,000 pounds. Dire wolves hunting in packs of dozens. Enormous bison with horn spans of 7 feet. Terror birds, flightless predators 10 feet tall with beaks like axes. This is the Pleistocene world. Earth's last ice age. A planet locked in deep freeze for over 100,000 years. And living in this frozen wilderness, scattered in small bands across the habitable zones, are humans. Your ancestors. Not primitive cave people fumbling in the dark, but sophisticated hunters with complex tools, elaborate clothing, art, and culture. They've adapted to the Ice Age so completely that this frozen world is all they know. It's home. If you're using this to fall asleep, that's exactly why I make these. So maybe subscribe and tell me, where are you right now and what time is it? I read the comments and it's fascinating. Seattle at sunrise, Chicago at lunch, Los Angeles at midnight, all watching the same story unfold. Drop a comment. I'm genuinely curious where in the world you are right now. So, humanity is thriving in the Ice Age. Animals are thriving. The world has found a brutal but stable equilibrium. And then, about 12,000 years ago, something changes. Something triggers an event so catastrophic, so rapid, so completely overwhelming that it will reshape every inch of the planet within a few human lifetimes. The ice begins to melt. Not slowly, not gradually. In geological terms, almost instantly. Within a few thousand years, sometimes within mere centuries, those mile-thick glaciers start collapsing. Ice sheets that took 100,000 years to build begin disintegrating in a cosmic blink. The meltwater has to go somewhere. Imagine the largest floods in recorded history, then multiply them by 1,000, by 10,000. Walls of water hundreds of feet high exploding across continents. Lakes the size of seas bursting through ice dams and draining in weeks. Coastlines drowning as oceans rise 400 feet, swallowing thousands of square miles of land where humans had lived for generations. And in the chaos, in the rapid transformation from ice world to the Earth we know today, something else happens. The giants die. Within a few thousand years, almost every large animal on the planet goes extinct. Mammoths, gone. Giant sloths, gone. Saber-toothed cats, terror birds, short-faced bears, dire wolves, massive bison, all gone. Over 150 species of megafauna, creatures that had survived multiple ice ages, that had thrived for millions of years, just vanish from the fossil record. This is the most dramatic extinction event since the asteroid that killed the dinosaurs. Except there was no asteroid. No single catastrophic impact. Just ice melting and seas rising, and something about that transformation killed the giants. But not humans. Somehow, impossibly, humans not only survived this planetary catastrophe, we thrived. We adapted. We exploded across every continent. And within a few thousand years of the Ice Age ending, we invented agriculture, built cities, created civilization. Everything you see around you, every bit of human achievement, traces back to what our ancestors did right at the moment the Ice Age ended. So what triggered the melt? Why did temperatures suddenly spike after 100,000 years of stability? What caused floods so massive they reshaped continents? Why did giant animals that had survived countless climate changes suddenly go extinct? And how did humans, relatively small and physically weak compared to the megafauna, not just survive but inherit the Earth? The answers are written in ice cores from Alaska, in sediment layers at the bottom of ancient lakes, in the scattered bones of extinct giants, and in the genetic code of every person alive today. This is the story of the most important climate transformation in human history, the moment when Earth stopped being an ice planet and became the world we know. This is what happened when the Ice Ages ended 12,000 years ago. 20,000 years ago, Earth was a completely different planet. Not metaphorically different. Actually, physically, fundamentally transformed from the world we know today. If you could somehow travel back in time to that moment, you'd barely recognize it as the same place. This was the last glacial maximum, the coldest, iciest period of the most recent ice age, and the world our ancestors inherited after their long evolutionary journey. Let's start with the ice itself, because that's what defined everything about this period. The sheer scale of the ice sheets that covered the planet is almost impossible to comprehend. We're not talking about glaciers in mountain valleys or ice caps at the poles. We're talking about continental ice sheets, miles thick, covering millions of square miles, reshaping entire landscapes under their incomprehensible weight. The Laurentide ice sheet alone, centered on the Hudson Bay, covered virtually all of Canada, and stretched deep into what's now the northern United States. Imagine ice from the Arctic Ocean all the way down to New York, to Pennsylvania, to the Great Lakes region. In some places, this ice was over 2 miles thick. 2 miles of solid ice pressing down on the bedrock, warping the Earth's crust beneath it, grinding mountains into powder, scouring valleys hundreds of feet deep. Meanwhile, across the country, the Cordilleran ice sheet blanketed the Northwest. Washington, Oregon, Idaho, Montana, all buried under ice. The weight was so tremendous that the land is still rebounding from it today, rising measurably each year as the land slowly returns to its original shape. 10,000 years after the ice finally melted, the Rockies had their own massive ice sheets covering the peaks and the mountain ranges of the interior. The Sierra Nevada carried glaciers that made modern mountain ice fields look like decorations. South America had ice sheets extending far north from Antarctica, covering Patagonia and the southern Andes. All this ice represented something extraordinary. Earth's water doesn't disappear. It just changes location. Every drop of water locked up in those continental ice sheets had come from somewhere, and that somewhere was the ocean. Sea levels during the last glacial maximum were approximately 400 feet lower than today. 400 feet. Let that sink in. The entire geography of Earth's coastlines was completely different. This massive drop in sea level exposed enormous areas of what's now ocean floor as dry land. These weren't just narrow strips of beach. They were vast territories, entire subcontinents that don't exist anymore. In the north, a landmass called Beringia connected Alaska and Russia, where the Bering Strait is today. But Beringia wasn't just a bridge. It was a massive territory, maybe 1,000 miles from north to south, a completely distinct ecological zone that supported its own unique communities of plants and animals. Between Florida and the Caribbean stretched the Florida Platform, a low-lying plain that connected what are now islands into a continuous landscape. Archaeological evidence suggests this was prime territory for Ice Age hunters, rich in resources, crisscrossed with rivers, home to massive herds of grazing animals. In the Gulf of Mexico, the exposed continental shelf created a massive coastal plain, connecting Texas, Louisiana, and Florida into a single enormous landmass. California's Channel Islands were joined as Santa Rosa. The Gulf of California was smaller. The Mississippi River was a massive canyon. The entire map of Earth looked alien. But it wasn't just the ice and exposed land that made this world different. The climate itself had been fundamentally restructured. The massive ice sheets created their own weather patterns, distorting atmospheric circulation in ways that affected the entire planet. The jet streams, those rivers of fast-moving air that guide weather systems across the continents, were pushed far south by the presence of the ice. This meant that regions that are temperate today experienced Ice Age conditions then. The American South, normally mild and humid, had a climate more like modern Canada. The Mojave Desert, which today is one of the driest places on Earth, had a completely different rainfall pattern. Parts of what's now endless sand supported grasslands and scattered trees. The Amazon rainforest, that great engine of global biodiversity, was reduced to scattered refuge areas separated by dry savanna. Ocean currents were different too. The great oceanic conveyor belt that redistributes heat around the planet followed altered pathways. Cold water from melting ice edges created nutrient-rich upwellings in different locations, changing where fish populations concentrated, which affected where seabirds nested, which influenced coastal ecosystems in cascading waves of transformation. This was a world of extremes. Seasonal variations were more dramatic than anything we experience today. Winters in the Ice Age steppe could last 8 or 9 months, with temperatures that would kill an unprotected human in minutes. Summers were brief but intensely productive, an explosion of plant growth and animal activity compressed into a few short weeks when everything that was going to survive and reproduce had to do it fast. And in this transformed world, a completely unique ecosystem had emerged. This wasn't just a colder version of modern environments. It was something that has no real parallel in today's world. The Mammoth Steppe, as scientists call it, stretched in an almost continuous band from California to the Carolinas, the largest biome in Earth's history. Imagine endless grasslands, but not like the Midwest prairies. This was colder, drier, more open. Scattered stands of hardy trees, mostly conifers, broke up the landscape. In the summer, wildflowers would briefly carpet the ground in explosions of color. In winter, everything turned to frozen wasteland where only the toughest organisms could survive. And what organisms they were! The megafauna of the Ice Age, the great animals that dominated this frozen planet, they were unlike anything alive today. They weren't just cold-adapted versions of modern species. They were something else entirely, products of hundreds of thousands of years of evolution in Ice Age conditions. The most iconic, of course, were the woolly mammoths. These weren't just hairy elephants. They were perfectly engineered Ice Age survival machines. Standing up to 13 feet tall at the shoulder, covered in 2 layers of hair, the outer layer reaching nearly 3 feet long in some individuals, with curved tusks that could exceed 15 feet in length. Those tusks weren't just weapons or displays. Mammoths used them as tools, sweeping snow aside to reach vegetation underneath, breaking through ice to access water, even fighting off predators. Mammoth social structure was similar to modern elephants, matriarchal herds of related females and their young, males forming bachelor groups or living solitary lives. But their behavior was adapted to the extreme seasonality of the Ice Age world. They had to migrate constantly, following the brief pulse of plant growth across vast distances, their movements timed to the seasons with precision born of evolutionary necessity. And they weren't alone. Woolly rhinoceros, equally impressive, equally adapted, roamed the same grasslands. These were massive animals, some weighing over 6,000 pounds, with 2 horns, the front one reaching over 3 feet long in the largest individuals. Like mammoths, they were covered in thick woolly coats. Unlike mammoths, they were solitary and apparently more aggressive. Cave paintings and preserved remains suggest they were formidable animals that even the largest predators approached with caution. Speaking of predators, the Ice Age had produced carnivores that would make modern big cats look modest. Saber-toothed cats, multiple species of them actually, had perfected the art of killing megafauna. Their famous elongated canines, reaching 7 inches in some species, weren't for biting in the way modern cats bite. They were precision instruments for severing blood vessels and windpipes. A saber-tooth would grapple its prey, use its powerful neck and shoulder muscles to stabilize the target, then deliver a surgical strike to vital areas with those specialized teeth. American lions, larger than any lion alive today, hunted in prides across North America. Their prey base was different from modern lions. They targeted young mammoths, bison, horses, even rhinos when they could catch them vulnerable. Skeletal evidence shows incredible power. American lion bones are denser and more robust than modern lions, suggesting animals capable of bringing down prey that would be impossible for today's predators. In North America, dire wolves hunted in packs across the Ice Age landscapes. These weren't just big wolves. They were a distinct species, more heavily built than modern grey wolves, with bone-crushing jaws adapted for a different hunting strategy. While modern wolves rely on endurance and pack coordination to exhaust prey, dire wolves were more like hyenas, using raw power and strong jaws to disable and consume prey, including cracking bones to access marrow. And the prey they hunted, besides mammoths and rhinos, included an astonishing diversity of megafauna. Giant ground sloths, some species reaching 20 feet long when standing upright, browsed on trees and shrubs. These weren't slow, clumsy animals despite their name. Reconstructions suggest they were formidable, with powerful arms tipped with massive claws, capable of defending themselves against even the largest predators. Glyptodonts, basically enormous armadillos the size of small cars, were protected by shells made of thousands of bone plates fused into armor that could stop most predators. Giant beavers, 8 feet long, built dams and lodges in Ice Age rivers. Massive bison, with horn spans reaching nearly 7 feet, moved in herds across the grasslands. Short-faced bears, distinct from modern bears, roamed the plains, their populations so dense that thousands of individual bears used some areas over the millennia, leaving layer after layer of remains. These were mostly vegetarian despite their size and power, but their sheer mass made them dangerous when disturbed. In the southern continent, the megafauna was even more bizarre. Diprotodon-like creatures, massive relatives of the wombat, weighing over 6,000 pounds. Thylacoleo-like predators were possibly pound for pound the most powerful hunters that ever evolved, with a bite force that exceeded even that of saber-toothed cats relative to body size. This entire ecosystem, from the smallest rodents to the largest mammoths, was intricately balanced. The megafauna weren't just inhabitants of the Ice Age world. They were ecosystem engineers, actively shaping their environment. Mammoths knocked down trees, maintaining the open grassland environment that supported the herds. Their dung fertilized the soil and spread seeds across vast distances. When they died, their enormous carcasses provided food for scavengers and returned nutrients to the soil in concentrated doses. The grasslands themselves were unlike anything that exists today. Modern tundra is often marshy and waterlogged, supporting limited vegetation. The Ice Age steppe was drier, more productive, capable of supporting the enormous biomass of animals that depended on it. The combination of cold temperatures, low rainfall, and constant grazing pressure created a unique plant community dominated by hardy grasses, sedges, and herbs that could survive both the long winter freeze and the intensive grazing of millions of herbivores. And into this world, human beings had successfully inserted themselves, not just surviving on the margins, but thriving as apex predators and one of the most successful species on the planet. By 20,000 years ago, humans had spread across virtually every Ice Age environment, from the edges of the continental ice sheets to the tropical regions that had remained warm. But the humans living through the last glacial maximum were different from us in important ways. Not biologically. They were anatomically modern, with the same cognitive abilities we have today. But culturally, they had become specialists in Ice Age survival, developing technologies and strategies that made them perhaps the most formidable predators the planet had ever seen. In the northern plains, people were building sophisticated shelters from mammoth bones. These weren't crude windbreaks. They were engineered structures using hundreds of bones carefully selected and arranged, covered with hides, insulated with earth and turf. Some of these shelters were substantial enough to support multiple families through entire winters. Archaeological sites show evidence of central hearths, storage areas, even specialized activity zones for different tasks. The technology of Ice Age hunters was astonishingly sophisticated. Spear points were crafted with techniques that modern flint knappers struggle to replicate. The best examples show understanding of stone fracture mechanics that rivals modern materials science. They weren't just chipping rocks randomly. They were carefully shaping cores, removing precise flakes in predetermined sequences, creating weapons that combined maximum effectiveness with efficient use of raw materials. Otlotls, spear throwers that worked like extensions of the human arm, multiplied throwing power dramatically. A skilled hunter with an otlotl could launch a spear over 100 yards with enough force to penetrate thick hide. This meant humans could kill dangerous animals from safer distances, reducing the risk inherent in hunting megafauna. They developed specialized tools for processing kills, carefully designed scrapers for hide preparation, bone needles for creating fitted clothing, engraving tools for decorating objects with symbolic designs. Each tool represented generations of accumulated knowledge, refined techniques passed down and improved upon. But perhaps their most important innovation was social. Ice Age humans lived in larger, more interconnected groups than their ancestors. They maintained trade networks that moved raw materials hundreds of miles. Flint from specific quarries shows up in tools at sites separated by weeks of travel. Seashells from the Atlantic coast appear in inland sites in the Midwest. Obsidian from the Rockies is found in the East. This networking meant more than just material exchange. It meant information sharing. A technique developed by one group could spread across thousands of miles within a generation. Innovation could accumulate faster than ever before. When someone figured out a better way to treat hides, or a more effective hunting strategy, or an improved shelter design, that knowledge could propagate through the entire human population. They were also developing sophisticated symbolic culture. Rock art from this period shows remarkable artistic skill and deep observation of animal behavior. The famous paintings at ancient sites weren't crude stick figures. They were nuanced, dynamic representations that captured the essence of Ice Age animals with accuracy that demonstrates intimate knowledge of these creatures. Carved figurines, musical instruments made from bone and ivory, decorative beads and pendants, all suggest people who had time for more than just survival. They were creating culture, passing down traditions, developing distinct group identities. Different regions showed different artistic styles, different tool-making traditions, suggesting the emergence of what we might recognize as ethnic or cultural groups. And they were successful, wildly successful. Human populations during the last glacial maximum numbered in the hundreds of thousands, maybe even low millions globally. They occupied every major landmass except Antarctica. They had mastered environments from the Arctic to the tropics. They were hunting the largest, most dangerous animals on the planet and winning consistently. But their success existed in a precarious balance. The entire Ice Age ecosystem, with all its magnificent megafauna, all its vast grasslands, all its carefully adapted species, depended on one critical factor remaining constant: the ice. As long as the climate stayed cold, as long as the ice sheets remained stable, as long as the mammoth steppe persisted, this world could continue indefinitely. Species had been evolving in Ice Age conditions for hundreds of thousands of years. Humans had been perfecting Ice Age survival strategies for millennia. The frozen planet had become the normal planet. This was just how the world was. The humans living 20,000 years ago had no memory of any other climate. Their great-grandparents and their great-great-grandparents, going back hundreds of generations, had known only the Ice Age. The skills they practiced, the animals they hunted, the plants they gathered, all of it was perfectly tuned to this frozen world. But deep in the ice cores of Alaska, in the sediment layers of ancient lakes, in the growth rings of long-dead trees, a change was coming. Subtle at first, almost imperceptible. Slight shifts in solar radiation patterns. Minor variations in atmospheric circulation. Small changes in ocean currents. Individually, these changes meant nothing. Together, they represented the beginning of a transformation that would be so rapid, so dramatic, so utterly complete that it would destroy the Ice Age world forever and reshape the planet into something entirely new. The frozen planet, which had seemed eternal, was about to discover it was anything but. And the species that had adapted so perfectly to Ice Age conditions, including the most adaptable species of all, were about to face a test unlike anything their ancestors had survived. The great thaw was beginning. So there they were, 20,000 years ago. Modern humans, the sole survivors of 3 human species that had emerged from that ancient bottleneck. They had spread across the planet, from the southern tip of South America to the frozen steppes of the Yukon. They had developed complex languages, sophisticated tools, and social networks that spanned continents. They were perfectly adapted to the Ice Age world. And then everything started to change. The trigger wasn't obvious at first. There was no single moment when the Ice Age decided to end. No dramatic event that announced the transformation to come. The climate had been fluctuating for hundreds of thousands of years. Warm periods followed by cold snaps followed by brief respites. The humans and animals living through it had no reason to think this time would be any different. But it was different. Catastrophically different. The real cause of what was about to happen began not on Earth, but in the geometry of Earth's orbit around the Sun. It's one of those beautiful cosmic accidents that shapes everything about life on our planet, yet remains completely invisible to anyone living through it. Scientists call them Mason cycles, named after the mathematician who first figured them out in the 1920s. There are 3 of them, Three different ways that Earth's orbit and rotation shift over time, changing how much solar radiation hits different parts of the planet. First, there's eccentricity. Earth's orbit around the Sun isn't a perfect circle. It's an ellipse, sometimes more circular, sometimes more elongated. This cycle takes about 100,000 years to complete. When the orbit is more elliptical, Earth's distance from the Sun varies more dramatically over the course of a year, intensifying seasonal differences. Second, there's obliquity, the tilt of Earth's axis. Right now, we're tilted at about 23.5 degrees. But that angle isn't constant. It varies between 22.1 and 24.5 degrees over a cycle that takes 41,000 years. More tilt means more extreme seasons. Less tilt means milder ones. Third, there's precession, the slow wobble of Earth's axis. Like a spinning top that's starting to slow down, Earth wobbles as it spins. This wobble takes about 26,000 years to complete a full cycle, and it determines which hemisphere is tilted toward the Sun during which part of Earth's orbit. None of these cycles is particularly dramatic on its own. But when they line up, when all three happen to reinforce each other, they can push Earth's climate into or out of an ice age. For the past 2.5 million years, these cycles have been driving the planet through repeated glacial and interglacial periods. Ice ages would build up slowly over tens of thousands of years as the cycles aligned to reduce summer sunshine in the northern hemisphere. Less summer sun meant winter snow didn't fully melt. Year after year, the snow accumulated, compressed into ice, and eventually formed the massive ice sheets that covered half the continents. But the cycles didn't stop. They kept turning, kept shifting, and eventually they would align the other way. More summer sunshine hitting the northern hemisphere. Slightly warmer temperatures. Just enough to start melting the ice sheets at the edges. Around 19,000 years ago, that's exactly what started happening. The orbital geometry had shifted to a configuration that delivered more solar radiation to the northern hemisphere during summer. Not a lot more, maybe 5% compared to the coldest periods. But it was enough. The ice sheets that had been growing for over 100,000 years finally stopped advancing. The leading edges, those massive walls of ice that had been grinding south year after year, began to stabilize. For a few thousand years, not much happened. The ice sheets weren't growing, but they weren't dramatically shrinking either. They just sat there, enormous and apparently permanent features of the landscape. A human living through this period would have noticed nothing unusual. The world was still frozen. Winters were still brutal. The ice was still there, dominating the horizon like it always had. But underneath, things were changing. Summer melt was starting to exceed winter accumulation. Not by much, just a few centimeters per year at first. But those centimeters added up. Meltwater began trickling from the edges of the ice sheets. Small streams became rivers. Rivers carved channels through the landscape, channels that would carry even more meltwater as the melting accelerated. By 18,000 years ago, the retreat was undeniable. The ice sheets were shrinking. Sea levels began rising as locked-up water returned to the oceans. The process was slow, almost imperceptible on human timescales. maybe a meter of sea level rise per century, maybe 2 kilometers of ice sheet retreat per year. Nothing that would alarm anyone living through it. But it was happening. The great thaw had begun. Then came the moment when everything should have continued smoothly toward our modern warm period. The Mason cycles were set. The ice should have just kept melting steadily for the next several thousand years. But instead, something completely unexpected happened. 12,900 years ago, right in the middle of this warming trend, the planet plunged back into Ice Age conditions. In a matter of decades, possibly years, temperatures in the northern hemisphere dropped back to near glacial levels. The ice sheets that had been retreating suddenly stopped. In some places, they even started advancing again. Scientists call this the Younger Dryas, named after a small Arctic flower that suddenly reappeared in pollen records from this period. The name makes it sound gentle, even pretty. It was neither. The Younger Dryas was a climate catastrophe, a 1,000-year interruption in the warming that should have been impossible according to the orbital cycles. And nobody knows exactly what caused it. That's not quite true. We have theories, several of them, but the evidence is contradictory, controversial, and in some cases, downright bizarre. The Younger Dryas is one of the great mysteries of paleoclimatology, and solving it matters because whatever triggered it could potentially happen again. The most widely accepted theory involves the Gulf of Mexico and the North Atlantic, and the great ocean conveyor belt that circulates water around the planet. This circulation system depends on density differences. Warm salty water from the tropics flows north toward the Arctic, cools down, becomes denser, and sinks to the ocean floor. That sinking drives the entire conveyor belt, pulling more warm water north to replace what sank. But what happens if you suddenly dump massive amounts of fresh water? If you flood into the North Atlantic with enough fresh water is less dense shut down the entire circulation system. Around the time the Younger Dryas began, there was an enormous glacial lake sitting in the middle of North America. Lake Agassiz, named after Dr. Andrews, the geologist who discovered evidence of it. This wasn't a normal lake. At its maximum extent, it was larger than all the modern Great Lakes combined. It contained more water than all the lakes on Earth today put together, and it was held back by a massive dam of ice. The theory goes like this. As the ice sheets melted, this ice dam weakened. Then, around 12,900 years ago, it failed catastrophically. Lake Agassiz emptied into the Gulf of Mexico and North Atlantic in a matter of months, maybe weeks. Imagine all that fresh water, hundreds of thousands of cubic kilometers of it, suddenly pouring into the ocean. The resulting flood would have been biblical in scale, and it would have done exactly what the theory predicts: shut down the ocean conveyor belt, plunging the northern hemisphere back into cold conditions. The problem is the evidence doesn't quite fit. Some sediment cores from the North Atlantic show the right kind of freshwater flooding at the right time. Others don't. The timing is fuzzy, and there's evidence that Lake Agassiz had drained eastward into the Atlantic before the Younger Dryas started, not during it. So some researchers have proposed more dramatic triggers. In the early 2000s, a team of scientists presented evidence for something that sounds like science fiction: an asteroid impact. They found a layer of sediment dating to the start of the Younger Dryas that contained unusual materials. Nanodiamonds, tiny particles that form under extreme heat and pressure. Platinum and iridium in concentrations much higher than normal. Magnetic microspherules, little beads of melted rock. And most intriguingly, hexagonal diamonds that can only form during hypervelocity impacts. Their interpretation? Around 12,900 years ago, a comet or asteroid broke up in Earth's atmosphere and exploded over the North American ice sheet. The impact, or more likely series of impacts, melted enormous amounts of ice, caused widespread wildfires, and threw enough debris into the atmosphere to block out sunlight and trigger rapid cooling. The hypothesis is controversial, to put it mildly. Other researchers have questioned whether those unusual materials really require an impact to explain. Nanodiamonds can form in wildfires. Platinum anomalies might come from volcanic eruptions. The hexagonal diamonds? Some scientists think they're actually just terrestrial materials that were misidentified. But the impact hypothesis refuses to die because it keeps finding new evidence. Impact proxies show up in sediment cores from multiple continents. There's evidence of widespread burning across North America at exactly the right time. And there's a curious correlation. Many of the large mammals that went extinct during this period disappeared right at the Younger Dryas boundary. Then there's the volcanic theory. Some researchers point to massive eruptions during this period, events that could have injected enough sulfur dioxide and ash into the stratosphere to cool the planet significantly. There's evidence of major volcanic activity in the Pacific Northwest and Central America during the crucial time window. It doesn't sink as easily. If you flood the North Atlantic with enough fresh water, you can shut down the entire circulation system. Around the time the Younger Dryas began, there was an enormous glacial lake sitting in the middle of North America. Lake Agassiz, named after Dr. Andrews, the geologist who discovered evidence of it. This wasn't a normal lake. At its maximum extent, it was larger than all the modern Great Lakes combined. It contained more water than all the lakes on Earth today put together, and it was held back by a massive dam of ice. The theory goes like this. As the ice sheets melted, this ice dam weakened. Then, around 12,900 years ago, it failed catastrophically. Lake Agassiz emptied into the Gulf of Mexico and North Atlantic in a matter of months, maybe weeks. Imagine all that fresh water, hundreds of thousands of cubic kilometers of it, suddenly pouring into the ocean. The resulting flood would have been biblical in scale, and it would have done exactly what the theory predicts: shut down the ocean conveyor belt, plunging the northern hemisphere back into cold conditions. The problem is the evidence doesn't quite fit. Some sediment cores from the North Atlantic show the right kind of freshwater flooding at the right time. Others don't. The timing is fuzzy, and there's evidence that Lake Agassiz had drained eastward into the Atlantic before the Younger Dryas started, not during it. So some researchers have proposed more dramatic triggers. In the early 2000s, a team of scientists presented evidence for something that sounds like science fiction: an asteroid impact. They found a layer of sediment dating to the start of the Younger Dryas that contained unusual materials. Nanodiamonds, tiny particles that form under extreme heat and pressure. Platinum and iridium in concentrations much higher than normal. Magnetic microspherules, little beads of melted rock. And most intriguingly, hexagonal diamonds that can only form during hypervelocity impacts. Their interpretation? Around 12,900 years ago, a comet or asteroid broke up in Earth's atmosphere and exploded over the North American ice sheet. The impact, or more likely series of impacts, melted enormous amounts of ice, caused widespread wildfires, and threw enough debris into the atmosphere to block out sunlight and trigger rapid cooling. The hypothesis is controversial, to put it mildly. Other researchers have questioned whether those unusual materials really require an impact to explain. Nanodiamonds can form in wildfires. Platinum anomalies might come from volcanic eruptions. The hexagonal diamonds? Some scientists think they're actually just terrestrial materials that were misidentified. But the impact hypothesis refuses to die because it keeps finding new evidence. Impact proxies show up in sediment cores from multiple continents. There's evidence of widespread burning across North America at exactly the right time. And there's a curious correlation. Many of the large mammals that went extinct during this period disappeared right at the Younger Dryas boundary. Then there's the volcanic theory. Some researchers point to massive eruptions during this period, events that could have injected enough sulfur dioxide and ash into the stratosphere to cool the planet significantly. There's evidence of major volcanic activity in the Pacific Northwest and Central America during the crucial time window. But here's what makes the Younger Dryas so frustratingly mysterious. Maybe they're all right. Maybe it wasn't one trigger, but a perfect storm of multiple factors hitting at once. Orbital cycles setting up vulnerable conditions, ice sheet collapse flooding the Gulf of Mexico, an asteroid impact adding extra chaos, volcanic eruptions amplifying the cooling. All of it happening within a few centuries, maybe even a few decades. Whatever started it, once the Younger Dryas cold snap began, feedback loops took over and amplified everything. This is where climate science gets truly terrifying, because it shows how quickly things can spiral out of control once certain thresholds are crossed. The most important feedback involved ice and snow. Fresh white surfaces reflect sunlight back into space. Scientists call this the albedo effect. When the planet started cooling during the Younger Dryas, snow and ice began covering areas that had been bare ground or tundra. Those new white surfaces reflected more sunlight, cooling things further, allowing even more snow and ice to accumulate, which reflected even more sunlight. A runaway cooling spiral. Then there was the permafrost feedback, though this one ran in the opposite direction once the cold snap ended. Permafrost, permanently frozen soil, contains enormous amounts of organic matter, dead plants and animals that froze before they could fully decompose. When permafrost thaws, microbes wake up and start breaking down that organic material, releasing methane and carbon dioxide. Methane is a greenhouse gas about 25 times more potent than carbon dioxide. When the warming resumed after the Younger Dryas ended, massive amounts of permafrost started thawing across Alaska and Canada. The resulting methane releases would have accelerated the warming dramatically. Ice cores from Alaska show atmospheric methane concentrations nearly doubling during the period right after the Younger Dryas ended. Ocean circulation was another feedback loop. When the Atlantic circulation shut down during the Younger Dryas, it didn't just cool the northern hemisphere. It also shifted tropical rainfall patterns, changed wind patterns across the Atlantic, and even affected monsoon systems in Asia and Africa. When circulation resumed, all those patterns shifted again, creating weather chaos across multiple continents. Forest cover played a role too. During the cold snap, forests died back in many areas, replaced by tundra and grassland. Trees are darker than grassland, so they absorb more sunlight and warm the local climate. Losing forest cover meant losing another source of warming. But when temperatures recovered, forests expanded aggressively, their dark canopies absorbing sunlight and accelerating local warming. All these feedbacks interacted in complex ways, creating what climate scientists call tipping points, thresholds beyond which change becomes self-reinforcing and potentially irreversible. The scary part is we still don't fully understand where these tipping points are or what triggers them. The Younger Dryas proved that Earth's climate can flip between states incredibly quickly, faster than any gradual orbital forcing could explain. So how do we know all this? How can scientists reconstruct what happened 12,000 years ago with such detail? The answer lies in some of the most remarkable detective work in science. Multiple lines of evidence from completely different sources that all tell parts of the same story. Ice cores are the gold standard. Scientists have drilled into the ice sheets of Alaska and Greenland, extracting cylinders of ice that preserve a detailed record of Earth's climate going back hundreds of thousands of years. Each year's snowfall creates a distinct layer. By counting these layers, scientists can establish precise chronologies. By analyzing the ice itself, they can determine past temperatures. Bubbles trapped in the ice contain actual samples of ancient atmosphere, showing greenhouse gas concentrations. Dust and volcanic ash layers mark specific events. The ice core from Alaska shows the Younger Dryas in stark detail. Temperatures plunging by 15 degrees Celsius in less than a decade. Atmospheric methane crashing. Dust concentrations spiking as vegetation died back and winds stripped exposed soil. Then, 1,200 years later, temperatures rocketing back up even faster, possibly recovering half the cooling in less than 3 years. Sediment cores tell a different part of the story. Lakes and ocean basins accumulate layers of sediment year after year, each layer containing pollen, microscopic organisms, chemical signatures, and sometimes larger remains. These cores reveal how ecosystems responded to climate changes. During the Younger Dryas, pollen records show temperate forests in the Midwest being replaced by Arctic tundra within decades. Pine trees that had been advancing north suddenly disappeared from the record, replaced by dwarf willows and grasses. Marine sediment cores show how ocean circulation changed. The ratio of different oxygen isotopes in the shells of tiny sea creatures indicates water temperature and salinity. These proxies reveal exactly when the Atlantic circulation collapsed and when it restarted. They show where fresh water flooded into the ocean and how quickly it spread. Cave formations, stalagmites and stalactites preserve another record. They grow continuously from dripping water, and their chemical composition reflects rainfall patterns and temperature. Some caves in New Mexico have stalagmites that grew throughout the entire Ice Age and into modern times. The chemical layers in these formations show how monsoon patterns shifted during the Younger Dryas, proving the climate disruption wasn't just regional but global. Ancient DNA adds yet another dimension. Preserved in permafrost, sediments, and even the guts of frozen animals, DNA reveals which species lived where and when. It shows migration patterns, population crashes, and even diet changes. DNA from mammoth remains shows that their populations were already declining before the Younger Dryas, probably due to earlier climate warming, but that the cold snap and subsequent rapid warming delivered the final blow. Tree rings provide annual resolution for more recent parts of the record. Ancient logs preserved in bogs and lakes show growth patterns that reflect year-to-year climate variations. During the Younger Dryas, these trees show growth rates crashing. Right after it ended, growth explodes, trees adding centimeters of wood per year instead of millimeters. Archaeological evidence shows how humans responded. Settlement patterns changed dramatically. In the Mississippi Valley, people who had been living as mobile hunter-gatherers began settling into permanent villages right at the end of the Younger Dryas. The stress of rapid climate change might have pushed them toward agriculture as wild food sources became less reliable. In North America, the distinctive Clovis culture, known for their beautifully crafted spear points, disappeared at the Younger Dryas boundary, replaced by different cultural traditions with different technologies. Put all these lines of evidence together, and you get a detailed picture of the transition from the Ice Age to our modern world. But it's not a smooth transition. It's chaotic, violent, marked by rapid flips between climate states. And the most dramatic changes were still ahead. Because once the Younger Dryas ended, around 11,700 years ago, the warming didn't just resume. It accelerated. The feedback loops that had been held in check during the cold snap suddenly kicked in all at once. Ice sheets that had stabilized during the Younger Dryas began collapsing at unprecedented rates. Permafrost that had refrozen started thawing explosively. Ocean circulation that had weakened roared back to life. The world was about to transform faster than at any time in the previous 100,000 years. And standing in the path of that transformation were the massive ice sheets themselves, now unstable, fracturing, and preparing to release floods that would dwarf anything in human memory. The real catastrophe was about to begin. The ice was melting, and when billions of tons of frozen water start moving, they don't move gently. Around 14,000 years ago, as temperatures began their relentless climb out of the glacial maximum, the great ice sheets that had dominated the northern hemisphere for 100,000 years started to collapse. Not gradually, not predictably, but in catastrophic bursts that would reshape entire continents and drown the world humanity had known. The first thing you need to understand is the scale. We're not talking about ice cubes melting in a glass. We're talking about ice sheets 2 miles thick, covering areas the size of continents. The Laurentide ice sheet alone stretched from the Arctic Ocean to what's now New York City, from the Atlantic to the Rocky Mountains. It contained enough frozen water to raise global sea levels by 200 feet. And it was coming apart. But the water couldn't just flow away. The ice sheets had created a problem for themselves. As they grew, they had scoured the landscape beneath them, carving enormous basins and valleys. They had blocked river drainage patterns that had existed for millions of years, and as they melted, all that meltwater had nowhere to go. It pooled. It accumulated. It formed lakes of truly mind-boggling dimensions, trapped behind walls of ice that were themselves slowly disintegrating. The largest of these was Glacial Lake Agassiz. If you took all 5 Great Lakes and combined them, you'd have something less than half the size of Agassiz at its maximum extent. This single lake covered parts of what are now Manitoba, Ontario, Saskatchewan, North Dakota, and Minnesota. It was 700 miles long, 250 miles wide in places, and in some spots over 2,000 feet deep. It contained more fresh water than all the lakes on Earth combined today, and it was held in place by a dam made of ice. Think about that for a moment. A body of water larger than the Great Salt Lake, restrained only by frozen barriers that were actively melting in the warming climate. The ice dam didn't need to melt completely. It just needed to develop a crack, a weak spot, one breach that would allow the pressure behind it to do the rest. Around 13,000 years ago, somewhere along the southern margin of the ice sheet, that breach occurred. What happened next was apocalyptic. The initial failure would have been sudden, probably triggered by a particularly warm summer or a seismic event from the rebounding continental crust. Once the breach formed, the pressure of billions of gallons of water behind it would have widened the gap in minutes. Within hours, a relatively small leak would have become a torrent carrying ice blocks the size of houses. Within days, the entire southern section of the ice dam collapsed. Lake Agassiz didn't drain. It exploded. Water roared out of the breach at volumes that dwarf anything in modern experience. The Mississippi River, one of the largest rivers on Earth, moves about 600,000 cubic feet of water per second. During the peak of the Agassiz outburst, water was flowing at rates estimated between 15 and 30 million cubic feet per second. That's 25 to 50 times the volume of all the rivers on Earth combined, concentrated into a few catastrophic weeks. The floodwaters carved new channels hundreds of feet deep through solid bedrock. They carried boulders the size of buses for hundreds of miles. They stripped away topsoil that had taken thousands of years to form, leaving behind the scoured, lake-dotted landscape of the Canadian Shield that exists today. Any human settlements in the path of this deluge were simply erased. No warning, no time to escape, just a wall of water and ice moving faster than a person could run, obliterating everything in its path. But the destruction wasn't limited to the immediate flood zone. All that fresh water had to go somewhere. Much of it flowed south down the Mississippi Valley and into the Gulf of Mexico. But other outbursts, at different times, drained east through the Great Lakes and down the St. Lawrence, or north into the Arctic Ocean. Each time, billions of gallons of fresh meltwater dumped into the ocean in geological instants. And this was just one lake. Across the northern hemisphere, dozens of similar ice-dammed lakes were forming, filling, and catastrophically draining. Each one represented a potential disaster. In the Pacific Northwest, an even more dramatic series of floods was remaking the landscape. Glacial Lake Missoula, though smaller than Agassiz, was positioned in a way that made its outbursts uniquely destructive. The lake formed in what's now western Montana, dammed by a finger of the Cordilleran ice sheet that pushed south from Canada into Idaho. As the climate warmed, this ice dam would fail, the lake would drain catastrophically, then the ice would advance again, the lake would refill, and the whole cycle would repeat. This happened at least 40 times over the course of 3,000 years. Each Missoula flood released about 500 cubic miles of water in a matter of days. The floodwaters funneled through narrow mountain valleys, accelerating to speeds of 60 miles per hour. When they hit the relatively flat Columbia Basin in eastern Washington, they spread out across 3,000 square miles, creating a temporary inland sea hundreds of feet deep that drained in less than a week. The power of these floods was incomprehensible. They ripped 1,000-foot deep gorges through solid basalt. They created waterfalls 3 times the height of Niagara Falls that existed for days and then vanished. They carved enormous amphitheater-shaped valleys called coulees, features so massive that early geologists couldn't understand what could have formed them. They transported house-sized boulders hundreds of miles from their sources. They left behind bizarre erosional features called the channeled scablands, a landscape so unique that it looks like something from another planet. For any humans living in the region, each flood would have been a civilization-ending event. Imagine seeing the horizon darken with an approaching wall of water 400 feet high, moving at the speed of a galloping horse, carrying ice and rock and uprooted forests. There would be no high ground to reach, no way to outrun it, nowhere to hide. Communities that had existed for generations would simply cease to exist, their only trace perhaps a few scattered stone tools found centuries later in flood deposits. But these dramatic outburst floods were only part of the story. They were catastrophic, but relatively brief. The real transformation was happening more slowly, but far more permanently. The seas were rising. As the ice sheets melted, they returned water to the oceans that had been locked away on land for 100,000 years. This wasn't a steady, gradual process. The rate of sea level rise varied dramatically depending on how fast the ice was melting. But the overall trend was relentless and unstoppable. Between 20,000 years ago and 8,000 years ago, global sea levels rose approximately 400 feet. That's a 40-story building's worth of vertical rise. 400 feet doesn't sound like much when you say it quickly. But think about what it means. Every low-lying coastal area, every river valley within hundreds of miles of the ocean, every island or peninsula that wasn't high and steep, all of it went underwater. And the flooding didn't happen all at once. It happened slowly enough that each generation might only see a few feet of change, but fast enough that within a few human lifetimes, the landscape of childhood would be completely unrecognizable. For the human populations living through this, it must have seemed like the world was ending in slow motion. The best hunting grounds, the richest fishing areas, the most productive gathering sites were all along coasts and rivers. These were the areas that flooded first. Generation after generation, communities would be forced to move inland, to abandon settlements that had been occupied for centuries, to learn new survival strategies in less productive territories. Nowhere were these losses more dramatic than in the places that simply ceased to exist as land at all. The Florida Shelf is one of the great lost places of human prehistory. For most of the last ice age, what's now the submerged continental shelf surrounding Florida was dry land. Not marginal tundra, but rich, productive territory. river valleys, wetlands, rolling hills, forests. Archaeological evidence suggests it was one of the most densely populated regions in Paleo-Indian America. The Florida Shelf was the heart of the Ice Age world in the southeast. Rivers that now drain separately into the Gulf, the Suwannee, the Apalachicola, all flowed together across this shelf into a single massive river system that emptied into the Gulf far to the south. The shallow seas that surrounded it were probably incredibly productive fishing grounds. The land itself supported herds of mastodon, giant sloth, and wild horses. For the humans who lived there, it was prime real estate. Then the seas began to rise. Initially, the changes would have been subtle. The coastal fishing areas moved slightly inland. Islands appeared where there had been continuous land. River mouths shifted. But by 10,000 years ago, the Florida Shelf was shrinking noticeably. What had been rolling hills became islands. River valleys became straits. Communities that had been inland suddenly found themselves on narrowing coastlines. By 8,000 years ago, the shelf was reduced to a few large islands. Archaeological sites from this period showed desperate adaptation strategies. People shifted to more maritime lifestyles, developing sophisticated boat technology and focusing on fishing and sea mammal hunting. But they were fighting a losing battle against the rising water. Around 6,200 years ago, the Florida Shelf may have suffered its final catastrophe. Geological evidence suggests rapid sea level rise finally submerged the remaining low-lying islands. Any communities that had managed to hang on despite the rising seas would have been swept away. Within a few generations after that, the last remnants of this lost world slipped beneath the waves permanently. Florida became a peninsula. The Gulf reached its modern extent, and an entire landscape that had been home to thousands of people for tens of thousands of years existed only in the sediments of the sea floor. We know about this lost land now only because fishing trawlers occasionally bring up artifacts from what were once dry land sites, mastodon teeth, stone tools, pieces of worked wood, evidence of a lost world. The same process was happening around the globe. Beringia, the vast landmass that had connected Alaska and Russia during the Ice Age, was slowly drowning. At its maximum extent, Beringia had been over 1,000 miles wide from north to south, an enormous plain that stretched from the Yukon to Siberia. The people who first colonized the Americas had walked across this land, following herds of mammoth and bison. As sea levels rose, Beringia shrank. The first areas to flood were the southern coasts, cutting off the easiest migration routes. Then the center of the landmass began to flood, creating an inland sea that eventually connected to the ocean. By 11,000 years ago, only a narrow bridge of land remained. By 10,000 years ago, that too was gone. The Bering Strait opened, and for the first time in 100,000 years, the continents of Asia and North America were completely separated. This had enormous consequences for the human populations on both sides. Groups that had maintained contact for thousands of years were suddenly isolated by 50 miles of ocean. The genetic and cultural exchange that had characterized human populations throughout the Ice Age came to an abrupt end. The peoples of the Americas and the peoples of Asia began diverging along separate evolutionary and cultural paths. all because the ice had melted and the seas had risen. But perhaps nowhere is the human impact of rising seas more potentially dramatic than in the Great Basin. Today, the Great Salt Lake is a remnant of a massive inland sea. But for most of the Ice Age, when the climate was wetter, the lake was known as Lake Bonneville, an enormous freshwater sea covering much of Utah. Its level was controlled by the mountains that surrounded it. As the climate warmed and glaciers melted, the lake level rose higher and higher. Around 14,500 years ago, the rising waters finally topped the natural barrier at Red Rock Pass in Idaho. What happened next was a flood that might have inspired some of humanity's oldest and most persistent myths. Water began cascading into the Snake River plain. Not gradually, but as a waterfall that would have dwarfed anything in the modern world. Calculations suggest water was pouring through the breach at immense rates, creating a roar that could be heard for hundreds of miles. The lake's level dropped by over 300 feet in a matter of weeks. The resulting flood scoured the Snake River Canyon, reshaping the landscape of Idaho forever. Any human communities in the path would have had no way to understand what was happening. This wasn't a seasonal flood that would recede. This was a catastrophic draining, a landscape-transforming event. Settlements, hunting grounds, all washed away or left high and dry as the lake receded. The flooding continued until the lake reached a stable level, leaving behind the much smaller Great Salt Lake we know today. In that time, vast areas of what had been a freshwater paradise became salt flats and desert. Archaeological evidence from the region shows a sudden shift in settlement patterns around this time, with populations adapting to a much drier, harsher environment. Some researchers think events like the Bonneville flood might be the origin of flood myths in indigenous cultures of the West. If you lived through it, you'd certainly remember. The Gulf of Mexico has yielded extensive evidence of submerged coastlines. Fishing trawlers regularly bring up artifacts, worked flints, bone tools, even occasionally human remains from what was once prime hunting territory for Paleo-Indian peoples. Beneath the waves lie the landscapes where our ancestors hunted mastodon and deer, gathered shellfish, and built seasonal camps. All drowned when the ice sheets melted and the Gulf filled in. Off the coast of Florida, archaeologists have discovered sinkholes that were fresh water pools 12,000 years ago, when sea levels were much lower and Florida's coastline extended miles beyond its current position. These pools were apparently used as burial sites by Paleo-Indians. Now submerged in 30 feet of water, they contain some of the oldest and best preserved human remains in North America. Every year, new sites are discovered. Underwater surveys using side-scan sonar and multi-beam mapping reveal ancient river channels, now submerged, showing where people would have settled. Stone tools and pottery appear in places that have been underwater for thousands of years. The archaeological evidence confirms what the flood myths preserved. Our ancestors witnessed and survived dramatic coastal inundation as the Ice Age ended. But here's where the story becomes uncomfortably relevant. Because we're not just looking at ancient history. We're looking at a preview of our own future. The warming that ended the last ice age raised global temperatures by about 4 to 7 degrees Celsius over roughly 10,000 years. That's an average warming rate of about 0.04 to 0.07 degrees per 1,000 years. Now, that might sound slow, But remember, it wasn't smooth. There were periods of rapid warming when temperatures jumped several degrees in just decades. The Younger Dryas termination around 11,700 years ago saw temperatures in Alaska rise by 10 degrees Celsius in less than 50 years. Current global warming is happening at a rate of about 0.2 degrees Celsius per decade. That's 2 degrees per century. 20 degrees per millennium, nearly 30 times faster than the average rate of warming that ended the Ice Age. We're compressing thousands of years of climate change into mere centuries. The ancient warming was triggered by orbital variations, changes in Earth's position relative to the Sun that gradually increased the amount of solar radiation reaching the northern hemisphere. It was natural, predictable according to astronomical cycles that have been operating for millions of years. Current warming is triggered by greenhouse gas emissions, carbon dioxide released from burning fossil fuels. It's anthropogenic, human-caused, and it's happening at a rate that has no natural analogue in the entire ice core record. Ice cores drilled from Antarctica and Greenland preserve atmospheric samples going back 800,000 years. They show us exactly what the atmosphere contained during multiple glacial cycles. Carbon dioxide levels during ice ages typically hovered around 180 parts per million. During warm interglacial periods, like the one we've been living in, levels rose to about 280 parts per million. This 100 ppm variation drove the entire cycle of ice ages and warm periods. Current atmospheric carbon dioxide levels exceed 420 parts per million. That's 50% higher than the highest natural levels recorded in the past 800,000 years. We've pushed the atmosphere into a state that hasn't existed since the Pliocene epoch, over 3 million years ago, when sea levels were 50 to 80 feet higher than today, and the Arctic was ice-free during summers. The ancient climate data teaches us something crucial about tipping points. Climate doesn't change smoothly and gradually. It lurches. Systems remain stable for long periods, absorbing changes and maintaining equilibrium, until suddenly they don't. They flip to a new state, often very rapidly. The ice core record shows this clearly. Temperature rise isn't a smooth curve. It's a staircase. Long periods of relative stability interrupted by sharp jumps. These transitions happen when feedback loops kick in. Ice melts, exposing dark rock or ocean that absorbs more sunlight, which melts more ice. Permafrost thaws, releasing methane, which warms the atmosphere, which thaws more permafrost. Ocean currents shift, changing how heat is distributed globally, which triggers further shifts. During the deglaciation, the climate system hit multiple tipping points. Each one amplified the warming, accelerated the ice loss, drove sea level rise faster. The scary part is that we can see similar tipping points approaching in our current climate. The Greenland ice sheet is losing mass at accelerating rates. Arctic sea ice is declining far faster than models predicted. Permafrost across Alaska and northern Canada is thawing and releasing carbon. Rainforests are experiencing more frequent droughts that kill trees and release stored carbon. The ancient warming was ultimately limited by negative feedbacks. Eventually the ice sheets melted completely, sea levels stabilized, and the climate reached a new equilibrium. But it took over 10,000 years, and along the way it eliminated most of the Ice Age megafauna and forced massive human migrations and adaptations. We're triggering similar changes, but faster, much faster. The question isn't whether sea levels will rise. They will. Ice sheets are already losing mass. The question is how fast and how far. Conservative estimates suggest 3 to 6 feet of sea level rise by 2100. More aggressive projections based on potential ice sheet instability suggest 10 feet or more is possible. Either scenario will inundate coastlines where hundreds of millions of people currently live. Our ancestors adapted to rising seas by moving inland, to higher ground, to new territories. They could do this because human population was tiny, maybe 5 to 10 million people globally at the end of the Ice Age. Most of the planet was empty. You could abandon a flooded coastal settlement and walk for a week to find unclaimed territory. We don't have that option. Earth now holds over 8 billion people. Most coastal land is already occupied, cultivated, built upon. Climate refugees in our future won't be moving into empty wilderness. They'll be competing for space in regions already at carrying capacity. The ancient climate transition also teaches us about ecosystem fragility. The megafauna extinctions weren't just about human hunting pressure. They were about ecosystems reorganizing, food webs collapsing. The relationships between species that had been stable for hundreds of thousands of years suddenly breaking down as climates shifted and habitats changed. We're seeing early signs of similar reorganization today. Coral reefs bleaching as ocean temperatures rise. Forest die-offs as drought patterns shift. Fish populations migrating toward the poles as tropical waters warm beyond their thermal tolerance. Species that can't migrate or adapt fast enough simply disappear. Once extinct, they're gone forever, just as mammoths and giant ground sloths and dire wolves are gone forever. The fossil record shows that major extinction events are permanent. The species lost during the end Pleistocene extinctions never came back. New species eventually evolved to fill empty ecological niches, but that process takes tens of thousands to millions of years. On human timescales, extinction is forever. But perhaps the most important lesson from the ancient climate transition is about human adaptability balanced against human suffering. Yes, our ancestors survived. They adapted their technologies, modified their hunting strategies, developed new food sources, and eventually thrived in the post-glacial world. The agricultural revolution, the rise of civilization, everything that followed was built on the foundation of post-glacial climate stability. But the transition period was brutal. Archaeological evidence shows increased violence, resource competition, population crashes, and the abandonment of entire regions. The genetic bottlenecks that show up in human DNA around this period indicate our population went through serious contractions. Many groups didn't make it. We're descended from the survivors, but survival came at enormous cost. The flood myths preserved in cultural memory aren't just about physical inundation. They're about loss. The loss of familiar landscapes, traditional territories, ways of life that had persisted for generations. They're about trauma. The trauma of abandoning ancestral lands, of watching the places you knew disappear, of uncertainty about whether you'd find new homes, new hunting grounds, new sources of food and water. Our ancestors survived by being flexible, mobile, and few in number. They could move when they needed to. They had technologies simple enough to rebuild from scratch if necessary. They lived in groups small enough to relocate relatively easily. These advantages allowed them to weather a climate transition that would have destroyed less adaptable species. Modern human civilization has different strengths and different vulnerabilities. We have vastly more sophisticated technology. We understand climate science. We can model future scenarios and potentially prepare for them. We have global communication networks, transportation systems, and institutional structures that could, theoretically, coordinate large-scale adaptive responses. But we're also far less mobile. Our infrastructure, cities, farms, factories, can't be easily relocated. We're dependent on complex supply chains that span continents. We've organized ourselves into nation-states with rigid borders and competing interests. And we're numerous, 8 billion people all needing food, water, shelter, and resources. The ancient climate transition took thousands of years. That gave ecosystems and human societies time to gradually adjust. Our current climate forcing is happening so fast that adaptation will be difficult for natural systems and human societies alike. We're not facing a gradual transition over many generations. We're facing dramatic changes within single lifetimes.